PT 726 Machine Learning. Hopefully you guys had a great weekend. The last time we talked about some neural network architectures. Well, we've actually began first talking about how neural networks, how the loss function with a neural network model is actually non-convex, and we visualize some of these contours for random as a function of some random weights. Then we began talking about neural network architectures. So we began with the residual connections, and we talked about them as a way of reducing the issues of vanishing gradients. So today we're going to continue talking about neural networks, and we're going to wrap it up and then talk about classification. Just an aside to begin with. So early stopping in training neural networks. So when we train neural networks, because the loss function becomes non-convex, we need to use iterative optimization algorithms. And then normally when we do that, we terminate the algorithm when the objective value or the parameter vector converges. Actually, sometimes in machine learning, especially when we're using neural network models, it's a good idea to terminate them earlier to avoid overfitting. And sometimes we do this by looking at, during training, we look at both the training loss as a function of the iterations, and also look at the validation loss as a function of the training iterations. And we kind of stop training when the validation loss starts to diverge from the training loss. So this is something that we sometimes do when we train neural networks. So that's just an aside. Now we're going to continue our discussion of neural network architecture, and we're going to talk about autoencoders.
Autoencoders are models of the form x hat equals g of z parameterized by some weights wl, L from 0 to capital L. So for the function g, the input is some vector z, and the output is actually x hat rather than y hat, which is what we're used to. So x hat is actually represents an approximation of the input. So now the input to the function g, z, is actually equal to some other function f of x, the input, parameterized by, the function is parameterized by some more weights, wl, from L, big L plus 1 to 2 big L plus 2. So here, f and g are neural networks, and typically the dimensionality of z is smaller than the dimensionality of x. So the way it works is that the input is x gets passed into f, known as the encoder, encodes the input x into z. So z is shown in the middle in this diagram, and z is called the code. The code z then gets passed into the function g, called the decoder, and the output is supposed to be something that is close to the original input x. So basically the input goes in, becomes the code through the encoder. The code gets decoded back into hopefully something very similar to the original input x. We call the output x hat. Usually the architectures of the encoder f and the decoder g mirror each other. So for example, in the diagram, we can see that from the input, as we go through the layers, we have fewer and fewer hidden units until we get to the code. In the decoder, as we go through the layers, we get more and more units or more and more neurons in every layer until eventually we get back to an approximation of the output. The output, which is an approximation of the input. Sometimes the decoder G has a sigmoid activation at the end if the data lies within a fixed range. So the sigmoid activation is commonly used to keep the output within a fixed range. Okay, so to train the autoencoder, we use this particular loss function. So the loss function is a function of all the weights from from index 0 all the way up to the last index. In this case, it's actually index 2 big L plus 2. And the loss is actually the square loss between the input and the approximate input, which is the output of the decoder. And to expand out what this x hat is, it's actually going to be g of f of xi. So we do this for every data point, calculate the square loss for each data point, and then we sum up over every data point. So here you can notice that there's only x, the input, and there's no y, the typical output that we see. So normally the data set consists of xi and yi, right? Now, to train the autoencoder, we actually don't even need any labels. We only need the inputs. So this is an example of unsupervised learning. So because the labels are not required, right? So previously we've been looking at supervised learning. So why do we do this? Well, autoencoders are used to compress data, and sometimes also to visualize high dimensional data in a lower dimensional space. So you will be doing some of this in assignment 3. You'll be coding up. You'll be using some code to train an autoencoder, as well as a variational autoencoder, which is kind of a more advanced version of autoencoders. In my own research, one area where we actually use autoencoders is in representation learning, in robotic decision making. So sometimes we would input images to a robot, and this image will be encoded into some lower dimensional code. This code is actually what the robot uses to make its decisions. So for example, we're hoping that by looking at the image, the robot through the encoder will be able to understand from the image some key features. For example, these features could be some understanding of obstacles, some understanding of its own position within the environment. Okay, and then based on this code, the robot will make a decision. Well, how do we know that the code is informative? We make sure that the code can be decoded to reproduce the original image. Right, so that's one example application that we use in research. Obviously, autoencoders are widely used in many, many different areas, not just robotics. Okay, so you'll be looking at this a bit more in your next assignment. So now that we're talking about images, I thought that it would be useful to give you a very brief introduction to data representation for images. So we've been talking about the input data as a vector x, right? So let's say we have a 9-dimensional vector x that could be the input, but a lot of times images appear in 2 dimensions. So for example, images are typically represented as a matrix. So this black and white image could be actually grayscale image might be represented as a matrix whose values are between 0 and 255, where 0 represents black and 255 represents white. Everything in between is going to be some shade of gray. Okay, so you can either think of this as a matrix or a vector if you vectorize it, if you kind of stack the columns of the matrix, or even the rows. With colored images, we would have 3 channels, red, green, and blue. Each of the channels could be represented by some matrix, each element of the matrix representing the strength of, let's say, red in every pixel. If you vectorize, if you kind of stack all the rows on top of each other, you would have a very long vector, basically. So a lot of times because humans, we just think of matrices representing images more naturally. We typically use the matrix representation more directly. When processing images, a very common architecture is the convolutional layers. So we're going to be briefly talking about this in the next few slides. For more information, you guys should consider taking the computer vision course. So let's begin talking about convolutional layers. So remember that our colored image is going to have some shape of height times width times 3, where the 3 represents the RGB color channels. So for example, if we have a 32 by 32 image, colored image, the input would be 32 by 32 by 3. And that's represented by this blue slab on the left. To kind of bring this input image to the next layer, we use filters or kernels. And the kernels are going to typically have a much smaller size, but the same depth. So the same height and width, a much smaller height and width. So here 7 by 7 in this case, but then the same depth. So 7 by 7 by 3 is our kernel or filter. And what we do with the kernel or filter is to slide it along this input image. So the first position that this filter occupies is over here. We do the inner product between the input image and the filter. So the inner product just means that we take every overlapping element, multiply them together, and then adding all of that up. The result will be a single number that is going to be stored in one of the elements in the next layer. So because our input image is going to be is 32 by 32, and our filter is 7 by 7, we can see that the resulting dimension here is going to be 26 by 26. Because we can only slide along, this image only 26 times in each dimension. So after we do the inner product, we can also take the activation function. We can also apply some activation function to get our result over here. Okay, so we slide along. So now we slide along the same filter to do the inner product, and then we get the next value here. And we keep going. So the filter actually is a bunch of weights that we need to train. So initially we may randomly initialize the elements of the filter. So these are the numbers that we do the inner product with the image. After training, these filters will have the appropriate weights in order to achieve a good training loss. So this is with one filter. By sliding along one 7 by 7 by 3 filter, we will be able to obtain in the next layer a matrix that is 26 by 26 by 1. So that's from one filter. We can also slide another filter along the same input image, and then we will be able to get a different 26 by 26 matrix, and we can have many more filters as well. So let's say we have 4 different filters, each of them 7 by 7 by 3. They're different because the numbers or the weights inside a filter are different, right? So in this case, we will obtain something that looks like 26 by 26 by 4 in the next layer. So this is kind of the idea of convolutional layers. You can repeat this. So now next time you're going to have something that is 26 by 26 by 4. So you could have some more filters, which could be, for example, 5 by 5 by 4. If you slide that filter along this intermediate layer, you will get the next layer and so on. So this is the idea behind convolutional layers and convolutional networks. So we won't really be going too much into this. I just wanted to give you guys a very quick preview, I guess. Definitely consider taking computer vision. So we can see that the filter size and the number of filters are hyperparameters that we can choose in convolutional networks. Some other hyperparameters include stride. So stride is basically how many pixels you skip over when you slide along the previous layer. We could also do zero padding to make the original input or make one of the layers bigger. We can also do dilation. That means that our filters are actually our filters are made up of not contiguous pixels. They may have holes inside them. Anyway, don't want to get into too much detail here. You will definitely learn more about this if you take the computer vision course. There are also something called pooling layers. So pooling layers, they are fixed functions. They're kind of like activation functions in that they're fixed functions. And these fixed functions can control overfitting, for example, by downsampling. So for example, if your input layer looks like something like this, we can use a max pool to turn every 2x2 block into the maximum value within that block. So for example, this input will give us this output. We take the maximum in each 2x2 region. We can also do average pooling, so that would be averaging, but the max pooling is probably the most common. So now when you see a diagram like this is a small VGG network, which is a convolutional network for processing images. So for object classification, image classification. So we begin with a convolutional layer followed by ReLU activation, and then convolutional layer followed by ReLU activation, right? And then we have a pooling layer. This repeats 3 times until we get to a fully connected layer. A fully connected layer is the same as the layer in the multi-layer perceptron. So then the output will give us the likelihood or the probability that the image is a certain object. If you look at papers, they will not only have a diagram like this, but they will also specify all the hyperparameters in each layer. Okay, so with that brief preview of autoencoders and convolutional layers, some things you will definitely learn more about in future courses. We're going to wrap up the unit on neural networks. Next, we're going to be talking about classification. So throughout the course, we have only been talking about regression. So now, classification. So motivation behind classification is that a lot of times we would like to categorize an observation. For example, is an email spam? What object is depicted in an image? So that's computer vision. Or what will be the next word? So that's natural language processing. The simplest case of classification is binary classification. So in regression, we would like the output of our model to match some value, some continuous value. But in classification, we just want to classify the input into one of the discrete classes. Right? So regression outputs a real vector, real meaning a vector with real numbers as elements. A classification model produces a class prediction. So such a model is also known as a classifier. So binary classification means that we just have 2 discrete classes. Okay, we'll be talking about binary classification models, which is known as a binary classifier. And without loss of generality, we're going to call one of the classes the positive class and the other class the negative class. We're going to have many data points, and the data points will have labels, which are going to be the positive examples. So labels which are positive are going to be called positive examples, and the data points with negative labels are going to be called the negative examples. So there are many different classification techniques. We're going to be focusing on the support vector machine. So this is actually a more of a traditional model, and by studying support vector machines, we can actually understand a lot more about optimization, linear algebra, as well as kind of different loss functions that one may use in machine learning. So this is actually a very good, very pedagogical topic to talk about support vector machines. So after we talk about support vector machines, we're going to move on to other techniques for classification. So let's take a look at the problem setup for SVMs. So that's what I'm going to be calling support vector machines, SVMs. Okay, so we're going to be given a data set xi, yi just as before. The main difference is that now the label can only take on 2 possible values, -1 and 1. We're going to be constructing a model called SVM to predict the label y from the data point x. Okay, so the model is very simple. It's just going to be a line in the case of 2D data. So here, so our data will consist of some, let's say, some positive examples, some negative examples, and our model will simply be a line that separates these two classes. In 3D, the separation boundary would be a plane, and in the case of higher dimensional data, we would determine a hyperplane. When we do prediction, so during training, we determine this line or hyperplane. During testing, we basically just say if a new data point lies on one side, we call it we predict the positive label, and if the new data point shows up on the other side, we predict the negative label. So that's the basic idea. This line or hyperplane is called the decision boundary. It separates the region where the model generates positive predictions and the region where the model generates negative predictions. And in the simplest form, support vector machines give us a linear classifier. A linear classifier is when the decision boundary is just a hyperplane. Okay, so maybe some of you have already noticed. If we have some data points with some positive and some negative examples, for the same examples, there might be many possible decision boundaries that will cleanly separate them. So which one should we choose? So the key idea in support vector machines is that we want to choose a boundary that is as far away from the data points as possible. So for example, this decision boundary. Why do we want to do that? Well, if we do that, then any noise in the data, so for example, these data might be in the actual data generation process, which we don't have access to, of course, there could be some noise. If we generate a line, if our model is a line that is as far away as any of the data points as possible, then we would be more robust to the noise. Intuitively, this is kind of less prone to overfitting, right? So even if these data points shift slightly, especially the other data points, the data points that are not the closest to the line, even if they shift slightly, the model will not change, right? The model is not sensitive to those noise. So that's basically the idea of support vector machines. We're going to turn that idea into a optimization problem. Okay, we'll work this out slowly. I'm going to be drawing some pictures. So hopefully you remember your geometry. So let's draw this graph x1, x2 versus x1. And then let's just consider any vector w. And then we're gonna consider any line that is perpendicular to w, right? Again, I'm not a good artist, but this is supposed to be perpendicular. The origin, we're gonna call that O. And then let's consider any point over here, which we call A. So now any vector, so this vector would be the vector OA. So now, because the line is perpendicular to W, we know that W transpose, the W vector transpose the vector OA, that should be equal to 0. In fact, any vector whose endpoint is along this line, so let's say that we call that X, well, W transpose X would be 0, right? So this line is basically, or this line, or more in generally the hyperplane, can be written as the set of points X such that W transpose X equals to 0. Okay, so basically, when we want to describe a line, we can use this set notation to describe the line. So that means that the line is parameterized by the vector W. So whenever we have a vector w, that basically corresponds to a line that is perpendicular to the vector w. Okay, so next, what if we don't want this line which passes through the origin? Okay, maybe draw another picture, right? Let's say we don't want this line which passes through the origin. So we still have the w here. Instead, we want a line that is maybe shifted up. It's the parallel line that is shifted up here. Okay, again, this is w. Let's put in our point A here. And then let's consider this point B, which we can get to from A if we travel in the same direction as W. Okay, so we still have the OA. So this is OA. This is AB. And then we still have W. Okay, should label the O. Okay, so remember that this line is going to be W transpose X equals to 0. That's what we just saw. That's what we just said on the left. So let's take a look at the point B, and let's do W transpose OB. Right. So this point B, so OB is going to be the vector going from O to B. And we're going to take the kind of the inner product of W with OB. So that equals to W transpose OA plus AB, which equals to W transpose OA plus W transpose AB. We know that W transpose OA equals to 0, and then W transpose AB, well, what is AB, right? AB is actually the same as W, right? So this is W, and then AB is just the same, exact same vector, right? It's same length, same direction, right? Exactly the same vector. So then this becomes W transpose W, which gives us the 2 norm of W squared. So now we have done this calculation without specifying which point B we have chosen, right? We could have chosen another B over here or some other B over here, and the calculation would have been the same. So this hyperplane is actually the set, has the property that W transpose X equals the 2 norm of W squared, right? If we want to use a set notation, then this hyperplane would be the set X such that W transpose X equals to the 2 norm squared of W. Okay, so we did this calculation assuming that this line here is moved up from the original line that passed through the origin by a distance of the norm of W. In general, we could have picked some other line, let's say this one, and suppose we pick the point B over here, then the only difference in our calculation is going to be that this vector AB will be longer. Right, so then this part will be longer, and basically if this part is longer, we will just have some other number at the end. Instead of W, instead of the 2 norm of W squared, we'll just have some other constant, let's say B. We'll just call it B, right? So any other arbitrary line that we can move back and forth, right? these lines are going to be have the property that W transpose X will be equal to B. As B increases, we move in this direction. So increasing B. As B decreases, we move in the other direction. So decreasing B. So that means that, so therefore, the set X such that W transpose X equals to B can define any hyperplane. Okay, so the shift up and down is, this is the translation. B gives us the translation, and then the vector W will give us the orientation, because the line is always going to be perpendicular to W. Okay, let's recap a bit. So we drew this graph and we said, let's pick some random vector, well, just some arbitrary vector W, and that would define some line which is perpendicular to W. In general, some hyperplane that is perpendicular to W. The line that passes through the origin was the set X such that W transpose X equals to 0, right? And that's simply because any point on any vector along the line will have an inner product with W that equals to 0. And then we did some more calculation and we said that, okay, suppose we draw a line which is translated up by the length of W. Through the math that we did, which is basically taking the inner product between W and OB, expanding OB, we have OA plus AB, right? And then W transpose OA gives us 0, so then we only have W transpose AB. While AB is the same as W, so then we had W transpose W, which is W, the 2 norm of W squared. And that basically told us that any point on this line, which is shifted up, is going to have the property that W transpose OB will be W, 2 norm of W squared. Okay, so this is basically like when B, in the general case, we have W transpose X equals B, and the B controls how much shift we have for the line, and W controls the orientation of the line. So the previous case was really when B equals the 2 norm of W squared. In the first case, it was when B is equal to 0, no shift. Okay, so hopefully that makes sense, right? So the main point is that any line which we want to use as the decision boundary can be described by a vector W and a scalar B. Okay, so we need to draw one more graph to understand distance to the hyperplane. Okay, so the same graph, but avoiding things being crowded, right? So remember we had the vector W, which basically gave us the direction of the hyperplane. So the hyperplane would be perpendicular to the direction of W. So now suppose we have some point X over here. We would like to find the distance to the hyperplane. So the distance to the hyperplane is basically this distance over here. And suppose that, let's just draw any point Z on the hyperplane and consider the vector going from X to going from Z to X or X to Z, doesn't matter that much. So in general, when you have a vector pointing in some direction and you would like to know the length of this vector in the direction, in some other direction, so that would be this length over here. So here's the X, and let's say the other direction is W. Then what you need to do is to basically, so distance So the distance is always going to be equal to the absolute value of, okay, I'm using too many of the same letters, so let's change the letters a bit. This is a more general linear algebra fact. So suppose you have some vector A, and you would like to know how long is A in the direction of B. So this distance is always going to be given by A, the vector whose distance we want to compute, transpose a unit vector in the B in the direction of B. So a unit vector in the direction of B is always going to be given by B, which gives us the direction of B, divided by the 2 norm of B. So in general, this is the formula for a distance. So on the left here, we would like to know the distance of x to the hyperplane. In other words, we would like to know how long is the vector from z to x in the direction of w. So in order to get this, we have to, so this is a distance, right? So the distance equals to the vector from z to x, so that is always given by x minus z, transpose a vector in the direction of w. So that's going to be w over the 2 norm of w, absolute value. Okay, and then we can simplify this a little bit. So that's going to be, well, first of all, we're going to pull the 1 over 2 norm of w outside here. And then inside we have x transpose minus z, x vector minus z transpose w, absolute value. And then we can continue by expanding out the transpose here. So that's going to be x transpose w minus z transpose w. Okay, or the other way, it doesn't matter. So previously we said that for any vector on the hyperplane, w transpose that vector will give us b, right? So that's what we said over here. So now applying that to our calculation, while z is a vector, is a point on the hyperplane. So z transpose w, which is equal to w transpose z, that's going to be equal to b. So in the end, we have 1 over 2 norm of w. So now I'm going to, I guess, reverse the order, which doesn't matter, minus b. So this is the distance from the hyperplane to x. So we'll be using this calculation a bit later to formulate the optimization problem for the SVM. Okay, so let's revisit this on the slide first. So we considered an arbitrary point z on some hyperplane. And of course, this hyperplane is going to be perpendicular to the direction of w. And we were just calculating the distance of some point x to the hyperplane. So we can do this by taking the inner product between the vector from x to z or z to x. I think we did z to x before on the written notes, but it's the same because of the absolute value. So we take the vector from x to z, and then we're going to do the inner product with a vector, with a unit vector in the direction of w. So that is going to be given by here. So simplifying this a little bit by first pulling out the 1 over 2 norm of w, and then multiplying the w inside the x minus z, we have this expression. And then finally, we simplify this expression by noting that because z is on the hyperplane, w transpose z must be equal to b. Okay, so finally, the distance from the hyperplane to x is going to be 1 over 2 norm of w times absolute value of w transpose x minus b. Okay, so that's kind of the mathematical background that we need to start to formulate the SVM problem. And the goal of SVM is to find the hyperplane that first separates the positive data points from the negative data points. And 2, we want the hyperplane to be as far away as possible from the data points. So the left plot here is more preferable because the hyperplane is really far from the closest red and blue points, right? And then this one is less preferable because the hyperplane is a little bit closer to the closest red and blue points. Okay, so that's why the distance to the hyperplane was an important calculation back here. So now we can start to write down the SVM problem. So first, some terminology. So let's take a look at this graph over here. We have some separating hyperplanes. So this is a decision boundary. The distance from this boundary to the closest data point is called the margin. And those closest data points are called the support vectors. So the support vectors are basically vectors that directly determine where the boundary should be, right? If you move these a little bit, the decision boundary might change. On the other hand, for the other vectors, which are not support vectors, you can move these a little bit and they won't really affect the margin or the decision boundary. Previously, we just derived the formula for the distance between any point x to the hyperplane. So that was over here, right? So from any point x, the distance from x to the hyperplane is going to be given by 1 over w 2 norm times w transpose x minus b absolute value, right? So we copy that over here. And then now we're going to consider xi, which is the ith data point. So all of these data points, xi, they have some distance given by this expression inside the braces to the hyperplane. And out of all of those data points, the ones with the minimum distance, so min over I of this expression, is called the margin. Okay, so we can use the variable m to denote the margin, which mathematically is going to be min over I of 1 over w 2 norm times absolute value of w transpose xi minus b. So that's the margin. So now we're ready to continue formulating the SVM problem. So we can now write down our criteria 1 and 2 mathematically, beginning with 1, which says that we want to separate the positive data points from the negative data points. Okay, so what does that mean mathematically? Well, we know that on the line, we have that w transpose x equals to b. Because we have a linear function here, that means that on one side of this line, w transpose x must be greater than b, and on the other side, w transpose x must be less than b. So we can say that for any points with label 1, so the positive data points, we want w transpose xi to be greater than or equal to b. And then for all of the data points with negative label, the negative data points, we want w transpose xi to be less than b. So that's kind of mathematically how we can write down the first criterion. Second, we want the hyperplane to be as far away as possible from the data points. So this means maximizing the margin, right? So we want to maximize the margin. So we want to maximize m, which equals to min over I of this distance of every data point to the decision boundary. So now putting everything together, we would like to maximize m by choosing the variables m, w, and b. So remember, w and b define the decision boundary. So we want to choose w and b such that the margin is maximized. Okay, so m can also be a decision variable as well. And then, so this is the objective. And then we also have the constraints. So we're subject to w transpose xi greater than or equal to b for all I such that yi equals to 1. So for positive examples, they should lie on one side of the hyperplane. And then W transpose Xi less than B for all I such that Yi is equal to -1. So this is for the negative examples. All of them should lie on the other side of the hyperplane. And finally, M equals to this expression, which is the definition of margin. So let's take a look at this a bit more slowly, actually. So we're now going to do the SVM formulation. And it's going to be a constraint optimization problem. So we would like to maximize the margin M subject to the first criterion, which says that W transpose Xi must be greater than B for all I such that Yi equals to 1. And then W transpose Xi less than B for all I such that Yi equals to -1. And finally, we have that the margin is defined to be min over the data points of 1 over W2 norm. So this is basically the distance formula from any point Xi to the decision boundary. So that's going to be absolute value of W transpose Xi minus B. Okay, so that's the formulation that we saw. So now we're going to just do a bit of math and manipulate things a little bit. So first I'm going to move things to give myself more room. And now I'm going to, well, maybe, yeah. So this used to be, the top one used to be less than B, so greater than B. So if I move the B over, I will have minus B greater than 0. And over here, I would have less than 0, right? So I'm just doing some simple algebra just to simplify the constraints a little bit. Okay, so next, I'm going to replace this margin definition with something a bit simpler. So here we're saying that the margin equals to the minimum distance from any data point to the decision boundary. So that's actually the same as saying that this distance, so the distance of every data point to the decision boundary, well, that must be greater than or equal to M, right? Because just by definition, M is the margin, and in particular, the margin must be greater than or equal to 0. So the last two statements can supersede this definition of M, so the M equals line, right? So you can think about that for a little bit. So these two are the same, right? So if the margin is the minimum distance from any data point to the hyperplane, that's equivalent to saying the distance of every data point. So for all I, the distance of every data point to the hyperplane must be greater than or equal to M. And then M must be greater than or equal to 0. So they're the same. So now we can use the last two statements to replace this one. Okay, just to make things a bit neater. So we're going to continue simplifying things. So the next thing we're going to do is to multiply on both sides for the third constraint, the 2 norm of W. Okay, so that one should be pretty straightforward. Okay, and lastly, we have this absolute value here. Well, maybe not lastly, but we're gonna split up this absolute value into its two cases. So to make some room for myself, I'm going to move things a little bit. Okay. So the first case for the absolute value is that we can just remove the absolute value. Right? So suppose that the inside of this absolute value is positive, then, well, we don't need to write the absolute value. Right? So that's the first case. The second case, so let me make more room here. So, or if we're in the second case, then W transpose Xi minus B should be less than or equal to minus M times 2 norm of W. Right, so if the absolute value is greater than this number, either the left-hand side is greater than the positive version of that number, or the thing inside the absolute value is so negative that it's more negative than the negative version of the right-hand side, right? So hopefully that makes sense. Okay, so we're just doing some math manipulations. We're not really changing anything. Okay, so now we can move things a bit. I'm going to move this part down. Okay, so before we had or and for all I. So it turns out that, well, let's start with the second case, right? So is the for all I really necessary here? Well, in this line, we have W transpose Xi minus B is less than some negative number. If you compare to this line, well, this is only possible when we have Xi when we have Xi data points with a negative label. Like so this line is only possible when the label is negative, right? Because if the label is positive, then we should be in the first case. So we can actually add with yi equals minus 1. So we're not losing anything by doing that. And similarly, in this case, in the first case, we have that W transpose Xi minus B is greater than some positive, greater than or equal to something non-negative. So this is only possible for all I with yi equals to 1. And of course, we can remove the or we had earlier because we must be in one of these cases. These cases are mutually exclusive. Okay, let's continue. So next, we can kind of compare this line with this line, and you kind of see that they're really saying the same thing. Well, one of them is saying left-hand side must be positive. The other one is saying, well, it should be greater than or equal to something that is non-negative, right? So assuming that W is not 0, then these two statements are saying the same thing. And same argument for these two statements. So we don't really need both of them. We can remove the first two and then just keep the last two. So let's do that. Okay, and then now moving everything up. Okay, so we can actually simplify things a little bit. So we're going to take a look at the first two statements. I'm going to make a bit of room here. So for the first statement, I'm going to do something really silly. I'm going to just say, okay, let's do 1 times this thing, W transpose Xi minus B is greater than or equal to M 2 norm of W. And for the second part, I'm going to multiply both sides by -1. So when I do that, well, the negative is gone. But for inequalities, whenever you multiply by a negative sign, you need to flip the inequality. So now, both of the first two lines, the first two constraints, are looking very similar. One of them says 1 times something greater than or equal to something. The other one says -1 times the same thing is greater than or equal to the same thing in the first line, right? And then the other difference is that the first line says for all I with yi equals to 1. The second line says yi equals to -1. Well, actually, if you look at what I just put in front, the 1 here would always equal to yi for the first line, and the -1 here would always be equal to yi for the second line. So now we can replace the 1 and the -1 in the front with yi. Okay, so now we have the same equation. These two look exactly the same. One of them says for all I with yi equals to 1. The other one says for all I with yi equals to -1. Right? So it turns out that these two cases cover every case. So we can remove this condition. We can combine these two lines and we can simply say for all I. And we don't need the second condition anymore. Okay, so took a bit of work, but now we have something quite simple. Okay, so hopefully that makes sense. We can still simplify further it actually. So the next thing we're going to do is to observe that, so observation. So if W, B, and if W, B, and M satisfy constraints, then we can multiply W by any number A, and we can multiply B by any number, let's say A, and then we keep M the same. So this also satisfy constraints. So we can basically always scale W and B by any constant, and we will not violate the constraints, right? And the reason is that if you put an A in here, and here in front, and also here, the A's will come out and all of them will cancel out. In addition, by scaling, and then the M's don't change, of course, right? So then there's no change there. In addition, not only do we not violate the constraints by scaling A and by scaling W and B, we can do it without changing the objective. So because of this, we can pick any scale. We can scale B and W any way we like. So we can arbitrarily scale W and B. Okay, so then we choose. So we're going to choose a scaling of W such that the 2 norm of W equals to 1 over M. Okay, and then so M equals 1 over W, 1 over the 2 norm of W. So now we can plug that into our formulation. Okay, so moving this up a little bit, so give me more room to write down the optimization again. So now the new formulation is maximize m. The variables we're going to be choosing to maximize m are going to be m, w, and b, and it's going to be subject to y, I. So remember, so we can either replace w or replace m, right? So we're going to replace m. So we're going to keep the w and b and then just rewrite m using a different scale. W transpose xi minus b is greater than or equal to 1 over 2 norm of w times 2 norm of w. And of course we know that that cancels, and it would just be 1 here. And of course we're still going to subject to m greater than or equal to 0. So we still had that before. Okay. So continuing, well, actually we have m equals 1 over 2 norm of w here. So let's erase that and replace that with 1 over 2 norm of w. And by the way, with this choice of m, we automatically satisfy m is greater than or equal to 0. So we don't need this part anymore either. Okay, so we're almost done. So now we're going to rewrite this one more time, and we don't really like this 1 over w, 2 norm of w in the objective. So we're going to flip it, and we're going to say, okay, let's minimize the 2 norm of w instead of maximize 1 over that, subject to yi times w transpose xi minus b greater than or equal to 1. And in fact, we can make this even nicer because the 2 norm of a vector is actually non-differentiable at the origin. So so that's not so good for optimization sometimes. Although it's not too big of a deal, but we can still make it nicer by squaring the objective to remove any non-differentiable points. And then, just for the sake of more convenient math later on, I'm going to add a 1/2 in front. Right, and then I'll move this over a little bit to make things neater. Okay, so this is the final. So this is the final SVM optimization problem. If we can determine a W, so minimize over what? Minimize over W and B. If we can determine a W and B that minimizes 1/2 times the 2 norm squared of W, that satisfies the constraint that for every data point, yi times W transpose xi minus b is greater than or equal to 1, then we would have found a decision boundary that separates the positive examples from the negative examples, and in addition with the maximum margin. Okay, so that was a lot of math. Let's take a look again at all the math on the slides after a 10-minute break. So take the 10 minutes to think about what we have covered, and then we'll review everything again. Okay, now let's take a second look. So we began our formulation with maximizing the margin, subject to this definition of margin. And then, so that was the kind of the second criterion that we talked about. The first criterion was that the data points must lie on one side with if they have positive label. So that was the first constraint. W transpose xi greater than b for all I such that yi equals 1. And then for all of the other data points, so the data points with negative label, they should be on the other side of the decision boundary. So W transpose xi less than b for all I such that yi equals to -1. The next step was to move the b to the other side. So subtracting b from both sides. Afterwards, the next step was to kind of work on this last constraint over here. So instead of saying m equals the minimum distance of all the data points to the hyperplane, that's actually equivalent to saying the distance of every data point to the hyperplane must be greater than or equal to m, the margin, and m is greater than or equal to 0. Okay, so next we did some simple algebra multiplying the third constraint by the 2 norm of w on both sides. And of course, this is we have to put in for all I for this constraint. I think I forgot to do that here. Okay, so the next step was to split up this absolute value into two cases. The first case is simply taking away the absolute value. So the inside being greater than or equal to this number is one case for the absolute value. The other case is that the inside here is so negative that it's less than or equal to the negative of the right-hand side. So that was the second case. Again, we keep the for all I. Okay, so now if you look at this, the first case can only happen for all the positive data points because this is greater than or equal to 0 for sure. And similarly, the second case can only happen for the negative data points. And that's because we have less than, this part is less than 0 for sure. So we can naturally split this into two cases again. One case with yi equals to 1, the other case with yi equals to -1. So now, the first and the third constraints and the second and the fourth constraints look very similar, and they become redundant, so we can combine them. We can simply remove the first two constraints because they are already covered by the next two. Okay, so next we did some kind of trivial things, multiply by 1 and then -1. When we multiply by the -1, we have to remember to flip the inequality as well. And by doing this, we can kind of see a yi in front here because the 1 and the -1 in front match the values of yi, so we can now bring in yi instead of the 1 and -1. And by doing this, we can see that, okay, this expression is now exactly the same, and the first constraint is for all positive examples, the second constraint is for all negative examples, and together they form all the examples. So we can combine everything into one line. So this should be for all I. Okay, so we're going to continue by noting that the constraint will remain satisfied if we multiply w and b by any number. And we can do that without changing the objective value, right? And we can show that by simply plugging in, we can replace w and b with alpha w and alpha b everywhere. And if we do some simplification, the alpha comes out on both sides. The alpha, we assume that it will be positive. Okay, so because of that, we get to choose any length for w itself. And we're going to be choosing the length to be 1 over m. Equivalently, we're choosing m equals 1 over the 2 norm of w. So now we can substitute this value of m in here. And notice that this m is definitely greater than or equal to 0. So we can also ignore the last constraint. Okay, so having done all of that, the right-hand side is going to become 1. Over here, this m is going to be 1 over 2 norm of w, and that's what we have over here. Next, we change the max to a min while flipping this objective. And then finally, we made the objective 1 over 2 times the objective squared, which doesn't really change. It doesn't change the optimal point when we transform the objective this way. And this was actually the final formulation for the SVM. So we started with something that looks kind of complicated, right? We said things in words where we had these two criteria. Okay, so this is already, so these two criteria, we kind of started to write down some math, but everything was a bit complicated. We also, even before this, we had to do some math to understand the geometry of the problem, right? But after all the mathematical steps, we actually get to a formulation that looks very simple. It has this convex objective with one constraint. Now let's review a little bit. So take a look at this. Which of the following statements about support vector machines are true? So why don't we take 2 minutes to look at this? Okay, let's take a look. An SVM is a binary classifier, so that's definitely true. An SVM is a linear classifier, also true. So we've been talking about using a single hyperplane to separate data from two different classes, right? So then the decision boundary of an SVM is a hyperplane, that's also true. Next, the decision boundary of an SVM may not pass through the origin. So this one is actually false, because we saw that in the case where b equals to 0, the decision boundary actually passes through the origin. So D is false. And E, the width of the margin is not known a priori. So this one is true. So we need to look at the data points before we know what the margin might be, right? Okay, and finally, an SVM tries to maximize the margin. So that's definitely true. So hopefully you got all or most of that. Okay, another one. Which of the following statements about SVMs are true? So again, take another 2 minutes to look at this. Okay, let's take a look. So A, maximizing 1 over 2 norm of W is equivalent to minimizing the 2 norm of W. Yeah, that's true. So maximizing something is equivalent to minimizing the reciprocal. Next, minimizing the 2 norm of W is equivalent to minimizing the squared 2 norm of W. So that's definitely true. The square function is actually non-decreasing, so that makes this one true. C, W is perpendicular to the decision boundary. This is again true. We covered that in the beginning with the geometry of everything. D, the decision boundary must pass through the origin when B equals 0. Okay, so just a reminder that this is true. So we just looked at that in the last review question. And lastly, maximizing the margin is equivalent to maximizing the squared 2 norm of W. Okay, so I'm going to be a bit careful here, but this one is false. Maximizing the margin is actually equivalent to minimizing the square 2 norm of W. Okay, so hopefully you got all of these as well. So what we have done so far is to formulate a constraint optimization problem that, when solved, will give us this particular this decision boundary, which maximizes the margin, as well as separates the positive data points from the negative data points. The constraint optimization problem was basically obtained after many steps of simplification and also learning about the geometry of the problem. So this was the kind of the final form of the constraint optimization problem. The previous techniques for optimizing a function, for example, the gradient-based methods, they actually will not work here because we not only want to minimize this function, we also want to minimize the function subject to constraints. So because of this, we need another way of solving this optimization problem. And so now we're going to take a quick aside to talk about Lagrange duality. So this is a concept that is general in the theory of optimization. In general, we are minimizing over some parameters theta of f of theta. So f of theta is the objective function. We have the constraints. That means we're subject to gi of theta being less than or equal to 0 for all I from 1 to k. So basically this means that we have k different inequality constraints. We also have L different equality constraints, hi of theta equals to 0. So first, some terminology. The set of parameters theta such that gi of theta is all less than or equal to 0 for all I, and hi of theta is equal to 0 for all I. So this just means that we're satisfying the constraints. This set of parameters, the set of parameters that satisfies the constraints, is called the feasible region. A solution theta inside the feasible region is known as a feasible solution. So the optimal solution would actually be a particular feasible solution, right? But most of the feasible solutions are probably not very good in the sense that they're not making the objective very small, right? But at least they're feasible. There are also many values of theta that are not feasible outside of the feasible region. So given such a generic constraint optimization problem, we can construct what's called the generalized Lagrangian, which basically turns a constraint optimization problem into an unconstrained optimization problem. The generalized Lagrangian is defined this way. So we're going to first talk about what it is and then talk about why we care about it. So here, the generalized Lagrangian is equal to f of theta, so this is the objective, plus sum over I from 1 to k of lambda I gi of theta, plus sum from I equals to 1 to L of nu I hi theta. So this this letter that looks like a V is actually the Greek letter nu. Okay, so what exactly does this mean? Well, first of all, we have the objective f of theta. Next, think of these other terms as penalizing, penalizing. So penalizing meaning making the entire thing bigger whenever we violate the constraint. So remember, our constraints are that gi should be negative, right? So if gi is positive, we're going to add a bunch of terms that are lambda I gi to make the overall sum bigger. That's kind of like a penalty on our objective, right? So before we just minimize objective, with the generalized Lagrangian, think of it as we want to keep this minimum, but we're going to get penalized whenever any of the GIs become positive. And similarly, the last term, the last summation, basically is saying that for any HI that are not 0, we're going to penalize the overall sum. Okay, so now consider this function phi of theta, and we're going to define that to be max over lambda and nu, but only so nu can be anything, but for the lambda vector, lambda i's must all be greater than or equal to 0 for all I. Okay, so we're gonna maximize this function that we defined over here. So this kind of formalizes the idea that these are kind of penalty terms, right? So let's take a look further. Actually, before that, one thing that will be really important to keep in mind is that whenever you have a function of many variables and you're maximizing this function, whatever variable that you're maximizing over will kind of make these variables disappear from the function. So for example, L is a function of theta, lambda, and nu. When we maximize over lambda and nu, the result is going to be just a function of theta, right? It's no longer a function of lambda and nu. That kind of makes sense, right? We want to pick the best or the best lambda and nu that will maximize this quantity, right? So after you have already picked the best lambda and nu, the result is going to be a function that is not a function of lambda and nu. It will be a function of whatever variable that remains, right? So this is phi of theta equals to this quantity here. Okay, so why did we define this? So it turns out that this function is exactly equal to f of theta, even though it looks a bit more complicated, right? So let's take a look at why. Okay, so let's think about how we can maximize this quantity in two cases. In the first case, let's suppose that GIs, all of the GIs are negative, right? All of the GIs are negative, meaning that we're satisfying the original constraints. In addition, let's imagine that all of the HIs are 0. Okay, so if all of the HIs are 0, then, well, we don't care about this. That whole thing goes to 0. In fact, this whole summation is 0 no matter what nu you pick. Okay, let's take a look at this part. So if we assume that GIs are all less than or equal to 0, how can we pick lambda to maximize L? If we're under the constraint that lambda, each of the components of lambda must be greater than or equal to 0. Well, if GI is less than or equal to 0, this thing is negative, right? So whenever you add anything positive for lambda I, you would be decreasing this L function, right? So this part is negative. If you multiply by a positive lambda I, you would be decreasing the overall value. So the best thing you can do if you want to maximize L is to pick all the lambdas to be 0. So when you pick all the lambda i's to be 0, then this whole thing becomes 0 as well, and you're back to f of theta. So that's the first case over here. So phi of theta actually equals to f of theta whenever all the constraints are satisfied. Okay, so think about that for a little bit. Okay, for the second case, suppose that not all of the constraints are satisfied. So for example, suppose that one of the, let's say G1 of theta, so one of the GIs is positive, right? So let's say maybe this one is positive. Well, if this is positive, how can we maximize L? Well, we would maximize L by picking the corresponding lambda I to be infinity. That would definitely maximize L, right? So whenever any of the constraints are violated, we can always pick one of the corresponding component of either lambda or nu to be infinity, to make this entire expression infinity. In the case of the GIs, if one of the GIs is positive, we pick the corresponding lambda I to be infinity. If HI is non-zero, for example, if HI is positive, we pick the corresponding nu I to be infinity, and that makes the entire thing infinity, right? That would definitely serve the purpose of maximizing L. On the other hand, if the HI is negative, we can pick the corresponding nu I to be negative infinity. Nu I does not have to be positive, so we can pick nu I to be negative infinity. So negative infinity times something negative, that will give us infinity. So that definitely will maximize L. So following that argument, we see that phi of theta is actually equal to f of theta whenever the constraints are satisfied, and it's going to equal to infinity otherwise. So that basically agrees with our intuition, right? So we want to minimize f while satisfying the constraints. So that means we can definitely minimize phi. So minimizing phi is the same as minimizing f, because when the constraints are satisfied, minimizing phi is exactly the same as minimizing f because they're equal. When the constraints are not satisfied, then in the previous optimization problem, well, definitely we don't want to pick that theta. We never want to pick a theta that violates the constraints. Similarly, we never want to pick a theta that violates the constraints because phi of theta becomes infinity. And that's definitely not how you minimize the function, right? If you're minimizing a function and you're getting infinity, well, that's not good. Okay, so that means that we can kind of define a few more terms here. So we're going to define P star to be min over theta of phi of theta. So P star is actually the optimal solution to our original problem. By defining phi, we can write P star to be equal to a single expression. Right, this is just kind of compacting the notation a little bit. And then we can also write down what phi of theta is. It is defined on this slide to be max over lambda and nu, where all the lambda components are non-negative, of this generalized Lagrangian L. Okay, so this is how we can write down the optimal solution to our optimization problem. Okay, so solving this problem, so this optimization problem is known as the primal problem. If we swap the max and the min, so if we maximize over lambda and nu first, and then minimize over theta afterwards, then the result is D star. We call this the dual problem. So in general, swapping optimization, like swapping the order of max min, will actually give you a different value. But in some special cases, it turns out that swapping these will not change the value, meaning that P star equals to D star. In that case, we can choose to either solve the primal problem or solve the dual problem. So we're going to be discussing that a bit later. So let's discuss weak duality. Okay, probably will make more sense to do this on the written notes. So weak duality relates P star to D star. So let's write those down. So P star equals min over theta, max over lambda and nu, where the lambda i's must be non-negative, of the L function, which is the Lagrangian, of theta lambda nu. And on the other hand, D star is the same thing, but with the optimization order swapped. So max over lambda nu, where lambda i's are non-negative, min over theta of L of theta lambda nu. So we're going to make a few observations first. So first observation, for all theta prime, so for all vectors theta, we have the property that L of theta prime, lambda, and nu is going to be equal, greater than or equal to min over theta of L of theta lambda nu. Okay, and also this happens for all lambda and nu as well, right? And that kind of makes sense because it doesn't matter what lambda and nu you look at. On the right hand side, we're minimizing over theta, right? On the left hand side, it's just saying, okay, for every theta that we might plug in into L, the result is going to be greater than or equal to if we minimize over theta, right? So that kind of makes sense. Okay, so that's number one. Okay, number two. So number two, we're going to look at this function min over theta of L theta L of theta lambda and nu. So remember that originally L is a function of theta lambda and nu, but now after maximizing over theta, this function is now just a function of lambda and nu. So suppose lambda 0 and nu 0 maximizes this function of lambda and nu. So this is kind of defining lambda 0 and nu 0, right? This is just they're defined to be the lambda and nu that will maximize this function. So now then we can write something kind of trivial. Then we can say min over theta of L of theta lambda and nu. If we plug in lambda 0 and nu 0, that's just the same thing as saying max over lambda nu min, so that's equal to max of lambda nu and min over theta of L of theta lambda and nu. Okay, so that one is just kind of using what it means to maximize the function. Okay, but then we can combine with 1. We can combine with 1 and then bring in for all theta. We have L of theta prime. For all theta prime, we have L of theta prime lambda and nu being greater than or equal to min over theta of L of theta lambda 0 nu 0. Right? So we're allowed to plug in the lambda 0 nu 0 here because in number 1, we said that was true for all lambda and nu. Okay, so we're going to continue. So let's make a separate observation, number 3, and that is for all theta prime. We have that max over lambda and nu of L of theta prime lambda and nu is always going to be equal to greater than or equal to L of theta prime, lambda 0, and nu 0. Why is that? Well, first of all, the lambda prime is just some variable that we're saying, okay, no matter what theta prime we consider. On the left hand side, we're choosing the lambda and nu that will maximize this L, right? On the right hand side, we simply plugged in a particular value of lambda and nu. In particular, what we're plugging in is lambda 0 and nu 0, right? So this is just a particular value of lambda and nu. So of course, it's going to be less than or equal to whatever will maximize L, right? So that's observation number 3. So putting everything together, we have number 4. For number 4, we're going to start with number 3. For all theta prime, we have max over lambda nu. I'm not very good at writing nu, so but it looks like a V. Okay, so max over lambda nu of L of theta prime lambda nu is going to be greater than or equal to L of theta prime lambda 0 nu 0. So that's observation number 3. And that is going to be greater than or equal to, so now using 2 now, right? 2 is saying for all theta prime, the first inequality holds. In particular, if we plug in lambda 0 and nu 0, the first part of this inequality still holds. So we can say this is greater than or equal to the min over theta of L of theta, lambda 0, nu 0. And then finally, this is equal to max of lambda, max over lambda and nu, min over theta of L of theta lambda nu. Okay. So I guess we don't need a lot of these. So we're gonna just keep track of just the first one, the first expression, and the last expression. So we know that for all theta prime, this thing must be greater than or equal to this thing. Okay, so now this expression is actually a function of theta. Remember, L used to be a function of theta, lambda, and nu, but after having maximized over lambda and nu, this is only a function of theta, right? So pick a theta prime 0 that minimizes this function. And this inequality would still be true. In other words, what we're really saying is that if we minimize over theta for this function, this must be greater than or equal to the last expression over here. So, and which turns out to be kind of the reversing the min and the max. Okay, just gonna write the whole thing. And it turns out that if you look back, actually we don't have to look back very far. We're just gonna scroll up a little bit. But when the min over theta appears first, well, that one is actually P star. And when we swap the order, that's D star. Okay, looks like we're out of time for today. So next time we're going to revisit weak duality on the slides. and then kind of continue to talk about how we can use weak duality to solve the constraint optimization for SVM. So I'll see you guys next time.